Party people, we're just going to keep powering through. I uploaded the link to Desmos for the 708, but you're like, but I'm watching this for something completely different, Mrs. Reynolds. Ooh, we're almost done. Look at this. 10 and 11, and here we go. Regression analysis. Ooh, okay. Let's take a look. We're also going to go look at our book because it's important. We need to also understand what they want us to talk about. We have these little mini lessons, and you get to listen to me randomly ramble, and we'll figure this out, review it together. So a lot of this, again, it's a lot of my focus and my degrees have been on probability and statistics, including my capstone project being a research and all that good stuff. So the points on a scatter plot usually do not fall on the regression line, which creates an error. Yes, residuals. Okay. Forgot about this. It's again, it's tedious if we did this by hand. So hopefully they again let us do it with technology, which is really where we're headed. We got to understand technology. We got to understand what it's doing, be able to check it, because technology fails. It's not always operator error that causes the problem. Sometimes it is the technology. Something's off. It spits out bad values, and we need to be able to spot that. But for the most part, technology is more efficient than our methods by hand or manual and all that kind of stuff. So residuals, the observed versus the predicted. Okay, so now for every single point, you have your input and your output. And so what you're doing is basically your output values, the actual values, minus the line. So let's take a look. So see this dot right here on 314. 3 is our input. Our output is 14. So 14 is the Y, not the Y hat. But the Y hat is going to be 10. So they're doing a different one. So you can read that example if you'd like. That's fine. So I'm doing this dot right here because it looked like nice, neat numbers. That's why my brain saw it. 14 is the actual output. 10 is the predicted output. So the error, the residual, is going to be 4. Just making sure, vocabulary wise. Yeah. The residual, E, is going to be 4. So so you find all of the residuals, all of the differences between the line and the difference here, and then you plot that. Then you plot that, which should be this next example. Let's go see. Aha. Ooh. Curved pattern state. Okay. If you remember in algebra, if you found the difference between consecutive points, you could figure out the degree of the function. Now this is perfect fits. So if you have perfect fit functions and you have a table of points, you could figure out the degree of the function by taking the differences, and then the differences. And when however many differences it took, say it took 4 subtractions of, don't worry about that. But anyway, there's some neat patterns that start to happen when we do math on top of math on top of math. We start to see how things are related in different ways if there's any type of prediction we can make. So here, error analysis. Lines, straight lines, are only one kind of line we have in our toolbox. We have quadratic regression, right? So maybe we have something that kind of increases till it hits a peak and then it decreases. And that's a better relationship between the two variables we're studying. We have cubic functions. We have all sorts of ways. We have exponential. We have, lots of ways to model the world around us and the relationships between different things in our world. So curved pattern, straight line is not a good fit. Random pattern, straight line is a good fit. Okay, so that's what they want. Some of the things that we do, it doesn't matter. Think about if all these dots were really close to this 0, the y equals 0. Anyway, for example, looking at a scatter plot shown, here we go. It appears like a straight line. Oh, this is beautiful. Look at this. But it looks like maybe a curved line. Notice they're not saying square or square root or exponential or anything like that. They're just saying curved is better than straight. So just keep that in mind. It looks pretty good, but then we look at the least squares, the residual plot. Look at that. Oh, very cool. Look, Caroline. And then it shoots back up. That's pretty cool. I think that's really cool. Quadratic exponent. Ah, ha, ha. Okay, so we're just going to focus on whether linear is or isn't a good fit. Okay, so that's our big overreaching goals for this unit. That's fine. I need to always take a look at that because I don't know how deep they want us to go. Looks like we're just going to get a peripheral, like an overview of our view copy of our ideas here. Okay, so a scatter plot with the least squares regression line is shown. Estimate the value to the nearest half unit. Okay, let's see. What is the predicted value for x? Predicted value. Okay, so at this point, we're going to look at x equals 5. Okay, good. Explanatory variables on the x-axis, response variables on the y-axis. I think I talked about that. We're going to look for the predicted value at x equals 5. So here's 5. We scroll up. 8. Because that's the line is the predicted value. The actual value is 11. So the residual is 3. So I would say 8. What is the predicted value? 8. Excellent. Okay. So now we're just kind of reading this stuff. We're thinking about, right, there's a predictive model and then there's our actual real life data. Feels like a very big difference, 8 to 3. And you'd have to really think about what your data actually was. They're just telling you X and Y, explanatory response, okay? Scatter plot with the least squares regression line is shown. Estimate the value to the nearest half unit. What is the observed value for x equals 3? Here's x equals 3. Well, the predicted would be 6, but the observed value looks like 4.5. Do you see that between 4 and 5? Woohoo! All right, we'll just keep going. This is what they want us to talk about. Let's talk about it. Scatter plot with the least squares regression line is shown. Estimate the value to the nearest half unit. Residual value. So we got to read. I'm reading carefully. I have a reading problem. If you worked with me live in class, you know that I suffer from reading problems. But it's okay because we can fix it. X equals 3. Explanatory. That doesn't sound... Oh boy, when that happens, let's see. Okay, so what is the residual value? We're going to look at x equals 3, the explanatory variable versus the response variable. But let's see, x equals 3 is 4.5, but the predicted value is 6, so that should be negative. So remember, we have our E is equal to our actual or observed value minus the predicted value. So at x equals 3, we have 4.5. Oh boy. Minus 6, which would be a negative 1/2. Let's go see. I can celebrate victories too. No, just because I'm the teacher, I didn't look at the answer ahead of time. I'm solving this just like I ask you to solve it. There's nothing special. Even my college professors, my favorite, Dr. Pranari, she was from Italy. She had her PhD in physics, and she taught my differential equations course at University of Colorado, Colorado Springs. She taught an in-person section and an online section, and it was fantastic. Her online version was just the recordings of her in-person versions. But she did problem sessions. Which are like this. Obviously, they were not our homework or quiz or test questions. They were extra questions that she would once a week record for an hour. Even if no student showed up live, she would still post them for her online students and her in-person students. Wonderful. I'm still not to the level of her caliber of instruction, both in person and for the way she handled her online portion of her course, but I'm going to get there. So, very, very good teacher. I don't remember why. Oh, if she had to solve, she has to solve the same way. She makes similar mistakes, but then she's way quicker at catching it. And then, we just do math and have fun. A scatter plot with the least squares is shown. Okay, which residual plot matches the scatter plot data? Cool. All right. Darn it. These are all going to be highlighted. So, okay, let's just kind of make I'm going to make up some. Over here, we're going to have, so let's do this. I'm going to try to draw it. That's right. I'm totally going to try to draw it. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Because this is -1, +1. Oh boy, that's a crazy looking 3. -2, -3, -4, so forth. Okay, so let's look at 1, 2, and on and on. We would have a -2. At 2, we would have a +2. Looks like at 3, we'd have like a -1/2. Oops. 4, we'd have a +1/2. 5, looks like we'd have a +3. 7, looks like we'd have a -2. And looks like we'd have a -1. So something like this. Again, I'm just looking at, so something like this. We have some, I can't scroll down. Let me see if I can scroll down to see it. But this is my residual plot, looking at the graph very quickly and estimating the differences, doing some mental math, and then trying my best to plot them. So something like this. Boop, 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 boop. Let's go see. Oh, man. All right, here we go. Bye, bye, bye. Okay, so some key things then. You only have 2 to choose from. That's great. So let's just pick, 1, 2, 3, 4. You have 4. Okay, it's not this one. They're all positive. See that? They're all above this 0, which isn't accurate. This one, let's take a look at 3. It's saying that at 3, we have a +3 residuals. So let's go see. At 3, it's below the line. That's a quick way. So we know it's negative. So we know it's not that graph. Hold on. This is frustrating. Let me spin back up so we can see more. 1 is at +2. Look, already 1 is at -2. Why? Not because it's at 2, but because here is the point of predicted value, and our actual observation is 1, 2, -2 below. So on our residual plot, we would expect this to be down here at -2. So it's not that one. Boom. Notice how this is at -2. It's that one. Even right here, it's at -1. Nope. All right. So that's how you can kind of read that. My graph. Testing yourself, pushing yourself to practice these skills is important, even if it is just for the exercise of application. The exercise of application. What's that? I'm so glad you asked. The exercise of application is that process by which we learn new things and we try to apply them ourselves. You do this every day in your life, and you've done it since you started walking. Since you were born, actually. You see things, you do things, you develop, you practice. You put them into practice, whether it is cooking or self-care, whether it is learning how to drive, you learn it and then you put it into application. So the practice of application is great. There's no better place to do this. There's no safer place to fail than school, or there shouldn't be a safer place to fail than school. We should encourage trying. We should encourage failing as long as students are trying their best, because that's how we learn and grow. And we teach our brain the great skills of just, all right, we fell off the bike, let's get back up. We fell off the skateboard, let's get back on it. I've gotten better through the years. I can now stand on a skateboard in my old age, which you thought, oh, when you're younger, you're so much better. Yeah, no, not for me. My brain, body, it just doesn't work. Last question. Here is a residual plot. Ooh, is the linear model appropriate for the scatter plot? Why or why not? What do you think? What do you think about this residual plot? Does it feel curved? Wow, those are some hardcore answers. No, there's an obvious pattern in the plot. Um, I have no idea if you talked about outliers, but you can totally look at an outlier if all of a sudden in your data there's something way far away from the rest of your points. But outliers do different things to our data. And maybe in your course you would have talked about this. We do remove outliers to make conclusions about our data. And one of the reasons we do that is because they can very much change our data. When you do that numerically, you need to tell the person about it. You need to say, hey, and you can even present the data with the outlier and without the outlier. I think we would have talked about this in unit 4 or 5 when we were just learning to do box plots and quartile ranges. If you did complete that exercise, which I think I even completed wrong, you create a box plot with the outlier and your 5 number summary, or your min Q1, median Q3, and max with the outlier and without the outlier, and then you can visually see how much our data changes. And a box plot helps you think about that. So anyway, outliers are still an important concept. We need to keep that in mind. Years ago, older people going to school, college, would have been considered an outlier. When I was in college, it was a crazy range of ages, crazy range. So we had people who were just retirees taking classes for fun. We had those who were trying to improve their career, so their midlife area. We had a lot of late 20s college students who didn't go to college right out of high school. Their parents couldn't help them, whatever reasons. And then you did have your typical college age student going to college between 18 and 22, right? All great, but it was very, very diverse when I went to college. I myself was one of those students. I was in my mid 20s, and then later in my later 20s when I finished my bachelor's degree and then pursuing my master's. Master's degrees are typically actually older, so it would be an outlier to have like an 18-year-old in a master's program. It's possible, it does happen. I went to school with a young graduate. Her name was Julianne, and she had finished her bachelor's degree by the age of 18, and she was in her master's program, and she was going to try to get her doctorate before she was 25. But she would be considered an outlier. So she would skew the data for the average age of students in these programs. And if we removed her from the data, we would explain why. All right. Obviously, those of you who are like, oh, okay, got the quiz. I turned this off. Those of you who are still listening, thank you. I'll end it here. I would say I see like a linear, possibly a parabolic relationships, like a parabola, right? We go down, we come here, we start to come back up. It could be exponential. I don't know. But don't worry about that. That's things for another time. Thanks for watching. Thanks for thinking. You can do anything you put your mind to.